Swayam Prabha. Digital India. Educated India.
So, hello and welcome everyone once again. What we are going to do is to take up where we left off last time, which is the discussion of measurement error, and what we discussed so far is measurement error in the dependent variable y, and we left off there, and we are going to take up measurement error in explanatory variables today. So, we consider the case where the measurement error is in x. And suppose, just like in the previous case, suppose that x star is the true value of x, which is unobserved, and what we do observe is a value of x, the capital X, which is given by x, which is the observed value, and hence also reported with error. So, in other words, the measurement error that we have over here is x minus x star, which could be of course greater than 0 or less than 0, and the equal to is a trivial case. So, what we are interested in estimating is the true relationship between x star and y, which is given by y equal to alpha plus beta x star plus u. But what we end up with is this relationship over here, where we are essentially estimating the effect of the observed x on y. So, once again we start with the assumption, as in the previous case of measurement error in y, exactly like that we start with the assumption that the measurement error is a mean zero error, meaning that for some observations there is a positive reporting error, and for some observations there is a negative reporting error, and that cancels out overall, so that in the end what we have is an average error of 0. So, recall that what we did in the previous case is that we considered the case where this is not equal to 0, and when this is not equal to 0, all that we end up with is a biased estimate of the intercept term alpha and nothing else. And because we are less interested in alpha, it really does not matter whether this is equal to 0, the expected value of E1 is equal to 0 or not, because that does not affect the estimation of beta. Okay. So, we maintain the OLS assumptions that our error term from the true equation is independent of x, the mean independence assumptions in other words is independent of both x and the observed value and the true value. So, x does not affect y after x star has been controlled for. So, essentially what we are saying over here is that x star is what y depends on, and once you know x star, the measurement error in x star does not really affect y. It also, when we replace x star by x, so we have this equation instead of the previous equation in x star. And once again, just like before, what we are saying over here is that we need to understand what happens to the estimation of beta when we replace the true x star by x. This is what we are saying. In the previous case, remember what we were saying is that if the measurement error is in y, then what happens to the estimate of beta when we replace the true value of y by the observed value of y. Now, in this case, when the measurement error is in x, we have two cases. Case 1 is when the reporting error is uncorrelated with the observed value of x. So, what we are saying is that the measurement error E1 is uncorrelated with observed x, so that the covariance of x and E1 is equal to 0. But recall that we had defined the measurement error as the difference between the true value of x and the observed value of x, which means that if E1 and x are uncorrelated, but E1 and x are in a and E1 and x star are in a linear relationship, it must be the case that E1 and x star are correlated, because otherwise you cannot have this linear relationship where both x and x star are not correlated with E1. So, E1 must be correlated with x star if we maintain the assumption that E1 is not correlated with x. So, the covariance x star and E1 is not equal to 0. Now, in this particular case, to determine whether the observed model satisfies the properties of the OLS, in other words, what we are trying to say is whether the observed model satisfies the mean independence condition, and hence does it lead to an unbiased estimate of beta, what we need to do is to rewrite the true model in terms of the observed value of x. So, we start with the true model y as a function of x star, and then use this equation over here where E1 equal to x minus x star and replace this in the true equation. So, what we end up with is y as a function of the observed value of x given by small x, but then we are left with an addition in the error term which is the negative beta E1. Okay. So, this is essentially what we are saying over here is that if you start from the true model and you incorporate the true the relationship between the true and the observed value of x, then what you end up with is a different error term. So, what we need to understand is whether, and since we are estimating this equation to get an OLS estimate of beta, what we need to understand is whether x is correlated with the new error term u minus beta E1. So, once again we maintain the Gauss Markov assumptions of the true model with respect to u. So, expectation u equal to 0 as per the OLS assumptions, and we also assume that expectation E1 is equal to 0 just like in the previous case, and this means that the expectation of the new error term should also be equal to 0, because each of the individual cases is equal to 0. The second assumption is that of conditional independence, and once again we assume that expectation of u given x is equal to 0, we maintain that assumption from the true model. And we just saw on the previous slide that case 1 is about the assumption of independence of x and E1. So, x and E1 are not correlated as per the case as per the first case. So, we also have this condition met over here, which is the expectation of E1 given x equal to 0, and once again these two combined means that the expectation of the new error term u minus beta E1 given x must be equal to 0. So, this is note that this is the revised conditional mean independence assumption that leads to an unbiased estimate of beta when we estimate beta using OLS. So, to summarize, both these conditions 1 and 2 taken together imply that beta hat is an unbiased estimate of beta, and then the first assumption also implies that alpha hat is an unbiased estimate of alpha. Further, if u and E1 are not correlated between themselves, which is, remember what we maintained from also in the previous case, we maintained the same assumptions in all the cases that we discussed. So, if u and E1 are uncorrelated, then what we have is the variance of the new error term has this additional term in there, which is different from the true model. The true model had only a variance term of sigma u square, but the revised model has this additional term in there, making the variance estimation higher than what we had in the true model. So, which means that when there is a measurement error in x, then the variance estimation or the standard error of beta OLS, beta hat OLS is going to be higher than in the case when there is no measurement error. Thus, except when, so this is typo on this slide, this should be sigma E1 square. So, this just means that thus except when sigma E1 square equal to 0, ME, the measurement error increases the error variance as before. This just means that the variance of the measurement error is equal to 0 or not. So, naturally we are considering the case where this is not equal to 0 and there is a measurement error. So, this increases the error variance, but does not affect the OLS estimate of beta, that remains unbiased. So, let us now take the second case, which is possibly the most interesting in the random measurement error issue, and this is basically saying that the reporting error is uncorrelated with the true value of x. Recall that case 1 was where the reporting error is uncorrelated with the observed value of x, and case 2 is where the reporting error is uncorrelated with the true value of x. Now, if E1 is uncorrelated with the observed value, now if E1 is uncorrelated with the true value of x star, true value x star of x, then what we have is that covariance x star and E1 is equal to 0. But once again, just like before, what we have is that E1 and there is a linear relationship between E1 x and x star, which means that E1 and x must be correlated when E1 and x star are not correlated. So, because E1 and x are correlated, what we have is that the covariance x given x and E1 is not equal to 0. So, this means that the conditional independence assumption is violated in the equation y equal to alpha plus beta x plus epsilon. So, this conditional independence assumption, so in this case the error term is just E1. So, this conditional independence assumption is violated, and this particular assumption that reporting error is uncorrelated with the true value of x and effectively it would be correlated with the observed value of x is called the classical errors in variables assumption. So, note that the covariance x E1, this is not equal to 0. So, we need to derive what this is equal to. This can be manipulated to be written as expectation of x and E1. So, what we have is expectation of x star plus E1 where we break x up into x star plus E1, and this is effectively equal to, because recall that we have already assumed that covariance between x star and E1 is equal to 0. So, which means that this is equal to 0. But then we are only left with the expectation of E1 and E1, which is essentially the variance of E1, which is represented by sigma E1 square. And we have another assumption over here that covariance of U and E1 is equal to 0, which you have seen in the previous two cases. Also, what we assume is that the measurement error, the random measurement error is not correlated with the error term of the true model. Thus, the covariance of x and E1 is the same as the variance of the measurement error under the classical errors in variables assumption. Okay. Once again, we maintain the Gauss Markov assumptions that expectation u and expectation u given x is equal to 0, which is essentially the conditional independence assumption from the true model. And recall that as in the previous case, what we can do is we can rewrite the true model in terms of the observed value of x, which just modifies our error term from u to u minus beta E1. Okay. This, what does this imply about the covariance between x and the new error term u minus beta E1? This is what we need to understand, remember, because this essentially gives you the CIA, the conditional independence assumption, and effectively determines whether the estimation of beta hat by OLS is biased or not. So, what we do is to take the expectation or the covariance between x and the new error term, and this can be rewritten as the covariance of x u minus the covariance of x and E1. Now, we have already assumed that this is equal to 0. So, what we are left with is minus beta times the covariance of x E1, and just to show you, in the previous slide we have already derived that the covariance of x and E1 is equal to the variance of E1. So, which means this is equal to minus beta sigma E1 square. So, now we need to measure the bias in the OLS estimate of beta. So, why do we start by saying that we are measuring a bias? It is already established that there is a bias when we write this condition over here, because as soon as we write that x and the new error term are correlated, we are essentially saying that the CIA or the conditional independence assumption is violated, and hence we cannot have an unbiased estimate of beta. So, we know that the estimate of beta is biased. Now, it is basically what we are left with is to estimate the extent of the bias in the OLS estimate of beta. So, this is precisely what we do on this slide, or what we start doing on this slide. We start with expectation of beta hat OLS, of course, and so basically we start with this condition x prime x, that beta hat is equal to x prime x whole inverse x prime y, and what you see in this first line in the first equation over here is that we have just expanded y from the regression model, and this is what we are left with. We are left with the beta plus the bias term, which is given by x prime x whole inverse x prime, the new error term, which is u minus beta E1. So, all we need to do is just to expand this term over here, which is not equal to 0, because x and remember what we just saw in the previous slide, that x and the new error term are correlated, and hence this is not equal to 0, and hence the expected value of beta hat does not converge to the true value of beta. Okay. So, when we expand this, what we get is this is equal to beta, the true value that remains, and the bias term can be rewritten as this is essentially the variance of x. So, 1 over the variance of x times, we already derived this on the previous slide, which is the relationship between x and the new error term, the covariance, and that we derived as minus beta sigma E1 square. And then just a few modifications, we take out beta, and this is equal to 1 minus sigma E1 square by sigma x square, and once again we just do a little bit more manipulation to make sense of what we have over here, and what we rewrite is the measurement error term, where recall that we started by saying that E1 is equal to x star minus x, and we rewrite that over here x in terms of x star and E1, and if you have this equation over here, this implies that the variance of x is equal to the variance of x star, which is the true value, plus the variance of the measurement error E1, and this is of course under the assumption that E1 and x star are not correlated, which is essentially the case 2 assumption, if you remember. Okay. So, this is what we have already done on the previous slide, and then we use this to once again simplify the expected value of beta hat to understand the extent of the bias, or the value of the bias to be more specific. And what we have is we just replace the variance of x by the variance of x star and the variance of E1, and then if you just simplify this once again, what you are left with is beta times the variance of x star divided by the variance of x. So, what is this? This is basically the variance of the true value of x divided by the variance of the observed value of x. Okay. Now, of course, the special case or the more trivial case, let us say, is that the variance of the measurement error is equal to 0, and note that in this very special case where the measurement error with the variance of the measurement error is equal to 0, what you have is the expectation of beta hat is basically tending to beta, and you do not have any bias. but of course that is a trivial case. We are interested in the case where this is not equal to 0 and there is indeed a measurement error, and this means that your expectation of beta hat OLS is equal to this value that we saw on the previous slide. And once again what you do is you replace this term over here, the variance of x equal to the variance of the true value of x plus the variance of the measurement error, and because this is positive, what you have is that sigma square x must be less than sigma x star square. Okay. And if this is the case, then what you have is that this value over here, which is the bias term, is less than 1. So, what we do over here is we start from what we saw on the left off in the previous slide, the expectation of beta hat equal to beta times the bias term, and once again what we see is that the variance of x is equal to the variance of the true value of x plus the variance of the error term. Now, of course, from this you can say that the variance of x is actually greater than the variance of the true value of x, and hence what you have over here is that the denominator is greater than the numerator, and hence the whole term must be less than 1. What this does is very important, because we can pinpoint that this bias term is going to be less than 1. What we can say is that the expectation of beta hat OLS, which is going back to this step over here, is less than the true value of beta, because the bias is less than 1, what you are multiplying beta by. And this is called the attenuation bias, the classic attenuation bias, which is equal to the ratio of the variance of the true value of x and the variance of the observed value of x. So, what we just saw is that a measurement error in the explanatory variable can have two cases. In the first case, where the measurement error is so what we just saw is that we consider the measurement error in explanatory variables two cases where the reporting error is uncorrelated with the observed value of x, which is the first case that we discussed, and in that case there is no bias in the OLS estimate of beta hat of beta, which is given by beta hat OLS, and the second case where the reporting error is uncorrelated with the true value of x and effectively it is correlated with the unobserved the observed value of x, and in this case we end up with a classic error in variable assumption, and what we end up with is an attenuation bias in the estimate, in the OLS estimate of beta. So, just a few more points. So, the OLS estimate of beta suffers from attenuation bias in the presence of measurement error of the CEV nature, which is the classical errors in variables. What we have done so far is to derive this and to show that this is an attenuation bias. Let us now try to understand intuitively why it is an attenuation bias. So, what we mean by attenuation bias is that the bias is going downward. So, the estimate of beta is actually lower than the true value of beta. So, imagine that it was only random error. So, imagine that the value of x that you observe has no true value of x in it, it only has random error. So, everyone, if you think of x as income, what we are saying over here is that everyone reports their income with error, and there is absolutely no income which is reported. Everyone, let us say everyone wants to evade taxes and then just cook up some value of income and report it to you. It has nothing to do with their actual income. In that case, what you have is x is completely measurement error. There is no true income in the variable x that you measure in the data. And suppose you are interested in the relationship between income and education outcome of children in a household. if the income variable that you capture is completely random error, in reality you should not expect any relationship between this variable and the children's education outcome, right. So, in that case what we are saying is that if suppose x was completely reported with random error or it is completely randomness, then the coefficient estimate of beta must be equal to 0, because we do not expect a correlation between this x, which is completely measurement error, and the y variable. So, in that case beta should be equal to 0, since x will then be uncorrelated with y. So, which means when you have full measurement error, your estimate of beta is completely attenuated to 0, but as you reduce the extent of the measurement error from complete randomness to a little bit of randomness and so on, what you are doing is you are going towards the true value of beta, right. So, what we are trying to do is to intuitively understand from the other side, where we start with complete randomness and then try to reduce the randomness and add that randomness to the true value. Another caveat is that the attenuation bias that we derived in the previous slide, recall, is the variance of the true value of x divided by the variance of the observed value of x, and then breaking this up in terms of the variance of the true value and the variance of the error term. What this means is that if the variance in x star, which is the true value, is very large relative to the variance in the measurement error, then the bias is small. What this means is that, so suppose you have collected data on income which is reported with error, but suppose the true income varies a lot in your sample and you have a big sample. So, there is a lot of variance in the true value of the income. If that is the case, and if the variance of this income is actually much larger compared to the variance in the reporting error, then the bias is reduced. Then you do not observe as much bias in your estimation of beta using OLS. Why? Because you are basically using the variation in your x, in your income, to estimate beta. And if this variation is just too large compared to the variation in the measurement error, compared to the measurement error itself, then the measurement error essentially fades out in the calculation of or in the estimation of the true value of beta. So, just to summarize what we did today is and in the previous class, which is combining the idea that there are possibilities of omitted variables, there are possibilities of measurement error, and we discussed cases where specifically the case of random measurement error, and both of these problems, the omitted variables and measurement error, we saw leads to bias. The reason we discussed these two specific cases is that these are possibly the most common occurrence when you deal with micro data, whether it is industrial data or farm data, whether it is in any sort of, let us say, development indicators in labor related studies, any kind of micro study that you want to do. Typically we face omitted variables and measurement error as the two most commonly occurring challenges in estimating the causal effect of a variable x on y. And what we said is that measurement error in general is possibly not a problem when the random measurement error is either in the explanatory variable, either in the dependent variable, or where the specific measurement error does not is not bound by the CEV assumption. Only in the case that the random measurement error follows the CEV assumption, which is basically that the random measurement error is related to the observed value of x, then it creates a bias in the estimate of beta. So, with that we end today's discussion, and this is until next class, where we would take up the idea of experiments. Thank you.